minutes.
Whoa. Recording has started. Good. And it doesn't say that it can't do my sound, so that's good as well. I'm going to go into Load Desktop of Magic and
Terms of vectors.
Fancy password. All right. So if you look at the handout, so we're talking about SIMD, which I'm not sure IBM uses that term as much as everybody else. They call it the vector processor for Z. And we had a vector processor back when, in the OS 390 days. And SAS actually used it. Mary Mace was involved in doing some of the work that had the compiler issuing commands that would do vector stuff. And it was kind of interesting. It was not used widely in the industry. I'd never seen an example of anybody using it. There were 16 32-bit vector registers, but each one of them had these things called extensions or elements. And you could, with a single instruction, depending on the size of the 3090 box that you had, would tell how many vector elements got updated with that single instruction. Now the problem was it was hardware dependent, so you had to sort of load from a control register to say how big the element size was, and everything you coded then was in a loop. And you would basically just sit there, and if you could do it in one, that was fine. Otherwise, you had to loop it if you were on a smaller box. So when you would send this thing to customers, you basically had to do it as a loop. Or you could sit there and maybe do, a lot of dual pathing and decide, which one you're going to branch to and stuff like that. So the new vector stuff is basically, I think, just IBM doing a catch up with Intel and doing SIMD processing the way that the other processors do. Came out in the Z13, which luckily we have, so we can test most of these instructions. The very newest POP is for the Z14, and it added some vector instructions that we don't have, and I found that out when I was doing my little demo to try to do the very first vector instruction that's described in the POP. Didn't work on our machine because it's new with the Z14. So the new SIMD stuff has these new registers. So this is really the first kind of major change that I can remember for Z, since 64-bit really. So they've new hardware registers, and they're 128 bits long. There's 32 of them. So in the instructions, you'll see how you code up to from 0 to 31 to indicate the vector register. And the other odd part about it is something that Joe mentioned to me that I hadn't realized before he mentioned it, was that the first 16 floating point registers actually overlay the first halves of the first 16 vector registers, which is just odd, and it causes some kind of weird things that we'll get into later. But I've got a slide later that kind of shows where the space of these things overlap. But you have to kind of be aware of that. If you're mixing floating point instructions with vector instructions, you have to realize that you probably should use vector registers 16 to 31. Then you're safe. You're not going to get any kind of collision on that. So depending on the instruction, you've got byte, half word, word. If you flip to the third page, we kind of show how a vector register is divided up. And you can divide it up any of those 5 ways. So you can treat the thing purely as a 128-bit value, and you can actually stick an extended floating point IEEE or hex float 128-bit, not hex float, it's only IEEE, a 128 extended format in those 128 bits, or you can have 2 what we call 8-byte or 64-bit, floats full, or you can have 4 words, or you can have 8 half words, or 16 bytes. And each of these things are, decimal or float or character or whatever it is, depends on the instruction. And sometimes the instruction itself will have an opcode that says what size you're looking at of the vector register. Sometimes there's a mask, and you have to look at the mask to know what size of the elements are within the vector register. So for this, it's all done in the registers. There's no kind of, let's do a vectorizing of memory and stuff like that. You load the thing into a vector register, then do the vector operation, then store it out someplace when you're done. And so there's a common format of these things. So let's go down to like page 4 where we see the overlay. So this is, I guess I could bring up the thing here. I'm talking and not going through it. Sorry, Joe. I've been assuming you were looking at my handout, which probably was stupid.
Thank you.
And sorry for everybody, watching this at home. Okay, so SIMD, return of the vectors, and then we got, this isn't your father's vector facility. So I basically just read these pages so we don't have to go through it again. But that's what it is. You can go to that share site and that page, and that's what I copied some of the stuff from here. But Share has had several sessions talking about the SIMD stuff, and IBM has some stuff as well.
Is that Bob Rogers' session?
Bob Rogers might have talked a little about it. Mostly he's talking about the things like
Pipeline.
caching and pipelining and all that other good kind of stuff. SIMD can take advantage of that, but doesn't have to have it.
Mm-hmm.
So on a single processor, you can still do this stuff. So you don't have to have multiple cores or anything else. So this is a sort of canonical look of the of what a vector register looks like with the quad word and the double word and all those other kind of things. And you're not going to mix and match. So it's going to be one of those rows or the other when you do a particular instruction.
What's the VA and VB mean?
Okay, this is like an example. So let's say that you had an instruction that dealt with bytes, and all the elements are bytes. So you've got 16 bytes, and you're going to do something with those 16 bytes in a vectorized way. So in this case, we've got vector register, they're calling it A, but just any vector register plus another vector register equals a third vector register. And each of these things are independent. So if you were saying we're going to add these two numbers together, these two bytes, and get a byte on the bottom, they don't overflow into each other. They're completely independent. So they go from 0 to 255, and that's it. But you can do add, subtract, or, XOR, all the other kind of normal instructions that you've got just based on the elements that you're in here. So SIMD stands for single instruction, multiple data. These are the multiple data that they're talking about.
Mm-hmm.
So here's the overlay. So thanks to Joe for pointing this out. You've got floating point registers that are only 64 bits long. And there used to be just 4 of them, were 0, 2, 4, and 6. And then somewhere along the line, they filled in the numbers so you could have 1, 3, and 5. But then they also added up, 7 through 15. And you have to, the next page we talk about, whether they're volatile or not. And that all has to do with the, how you call functions and whether the registers need to be saved across the function boundaries and stuff like that. So the thing to remember about this overlap is if you do any floating point operation that sets a floating point register, the part of it that's in the vector register, the corresponding vector register, is going to get zeroed out. And it's not, that it's going to remain random or remain what it was before. It zeroes it. So just be aware that if you do anything like a double divide or something like that, you say one of these things, and you've been holding some, number in this part of the vector register, that's going to get wiped out when you do the floating point instruction. But if you go 16 to 31, you're safe. All of these are not overlapped by the floating point registers. And that's basically just what I said. So here's the linkage convention. You just kind of think about it. If they're volatile, that means that you don't have to worry about, saving and restoring them across the function boundaries. And the weird part is, bytes, 0 through 7 are non-volatile. Bytes 8 through 15 are volatile. So it's a very weird thing. So mostly what I'm thinking is, let's just stick to 16 to 31, and then we've got half of them are volatile, half of them aren't, and you can just pick from there and not worry about running into the floating point problems. So the very first instruction, if you look at the POP, and I've actually got that down here. If you look at, let's say the POP, and we look at the instructions for vector stuff, here's the vector overview. The very first set, we've got integer, string, floating point, but these first ones that we've got are just sort of generic vector operations. Well, the very first one is instructions, and so I looked at that and I thought, well, let me just start at the top. So I went to vector bit permute. And you read this god-awful thing, and you can't tell what the hell it's supposed to do. A source vector is created from the concatenation of the second operand followed by 128 binary zeros. The byte-sized elements of the third operand contain unsigned integers which are used to select bits from the source vector to create a half-word result, which is placed in bits 48 to 63 of the first operand. Other half-words are set to 0. Each bit of the half-word result is selected from the source vector by the corresponding byte in the third operand. Yada, yada, yada. Very bizarre. And that, you think, okay, I might be able to figure out what that is if I read that paragraph 10 times in a row. But then you get down to this programming note. The fact that the source vector contains 128 bits of zeros following the second operand permits the permuted data to be selected from a 256-bit quantity using a single index register. Assume yada, yada, yada. You've got another register that's got 128 in each byte, and then you do these 4 instructions and you get something else. It's like, well, what on earth is that? So that didn't make any sense at all until I got back to this guy. So let's go back here. So vector bit permute, what are you really doing? So this isn't actually an instruction because I've got all 256 bits here. I don't have 128 followed by 128 zeros. Mm-hmm. But the idea is that you've got 256 bits, and now you want to sit there and pull out 16 of them and create a half word. And you get to pick any 16 of those 256 by way of these 16 bytes that basically have a bit position in each byte that points to one of the bits that you want to pull down. So you start thinking, well, there must be a reason they came up with this instruction. It seems kind of, arbitrary.
Encryption.
It's encryption. So really, I think what this came up with, if you look at the SHA-512 algorithm for hashing and stuff like that, he does stuff like that. It's like, figure out, the big prime number, the cube root of the biggest prime number, and multiply it by this, and you pull out those bits and this and that. I think this is what it's going to get down to. So as just a sample of this kind of thing, I put up this stuff. I left out a lot of the in-between bytes in here. But from 0 to 128, if you can think about that, that's going to be one vector register. From 120 or 0 to 127, 128 to 256 is another vector register. And then you've got this mask that pulls out the bits. And then basically you have to go to each one of these. So these aren't like byte offsets, they're bit offsets. So each of these numbers I wrote as decimal rather than hex. So the 24th bit, we're going to go and find where that is. Well, it's a hex 99, so that means the high bit is on. So that's going to pull out a 1. And then 201 goes over here. Okay, that one's on. That's the second bit in that byte. We'll put that one on. And so on. You go through them all, and you end up with the same. You end up with this answer. Well, the instruction says that it's only going to be 128 bits followed by 128 bits of 0. So there's no instruction, one instruction that will do this. So they did it in 2 pieces. So the first piece, well, we'll get to that later. First, I want to show you something that's common to all vector instructions. So I said that the vectors registers go from 0 to 31. Well, in normal 370 opcode assembler stuff, you've only got 4 bits to identify a register. So you can go from 0 to 15 and that's it. Mm-hmm. So when you look at these instructions in a dump or in an OMD or anything else, you're going to look at that register. It's always going to be, from 0 to 15, that 0 to F. Mm-hmm. So how do you know the ones that are 16 to 31? Well, there's this thing called the RXB. And it's at a fixed location in all these instructions. So every vector instruction, any of these things that start with a V, are going to have an RXB just before the last byte. And you really think of these things as this is the opcode and this is the second part of the opcode. So when you look in the index as far as opcodes go, that's how they're listed. Mm-hmm. But right in front of it is the RXB. It's 4 bits, and each of the bits corresponds to one of the vector registers that might be indicated in the instruction. Each instruction can have from 1 to 4 vector registers. So you've got from 1 to 4 bits in here that'll tell you whether you need to add 16 or not to this. So if you've got a 1 in the high order, then this one you have to add 16 in your mind to know what vector register that one's talking about. When you type out the instruction, the assembler is going to do this for you. Mm-hmm. So you don't have to create these opcodes and stuff like that. But it's just something to remember when you're looking at these guys.
Dumps are going to be fun.
Yeah. So yeah, when I was first looking at I actually did this because I needed to. The Z-Linux compiler, the IBM compiler that does this stuff, uses vector instructions. And when I was working on some problem, I had to divide, and I'm like, what the hell is that? I couldn't figure out what opcode it was. And finally, I got the new POP, and I'm looking, I'm like, oh, it's a vector divide. Why the hell is it a vector divide? But that led on. So we'll go on.
CPR is current with POP 14 on all the vector instructions.
And thank you very much for that. The other thing is that CPR will show you the first 8 floating point registers, like I said, but he'll only show the first half of the first 16 vector registers since they overlap. But it's still useful if you happen to have things, because the IBM code does use, vector registers 0 through 15. So if you're using CPR, you've got the vectors instructions, you'll at least be able to see half of the 128 bits as you're using CPR and stepping through this stuff. ASM IDF is the same way. They just show the floating point register. They don't show the vector registers. I'm assuming that's going to get fixed in a later release, but it's not there.
On LZX, I do show all of the vector registers.
Do you now? What is there a special instruction you have to do that, or is that just
There's
in the
a
regular
command
registers
you have to
play?
run. It's called VREG.
VREG. All right.
It'll dump them all out.
Very excellent. Very good. Thank you.
Don, does IPCS show all the vector registers?
I haven't tried IPCS, and I somehow doubt that it does, but that's something I can look at.
'Cause that's really
Well, the thing is,
kind of coming by.
we're only on Z-Linux, right? So there is no IPCS for Z-Linux. So we haven't really, come down to the point where we need something like that. GDB, I haven't looked at that either to know whether that's showing the stuff. I mean, that's really the other debugger device CPR that we're using over there. But it would be interesting to see if that does that.
Are we not going to have any way to take advantage of this on MDS?
We can take advantage of it right now on MBS if you wanted to, but the problem is that we've always we've done like architectural level sets. So the compiler that Joe and Kevin put out are set at a particular level set, and they arc level, and they're not going to go beyond that until we're sure that all the customers that we've got can handle that kind of thing.
Gotcha.
So we're always a few releases behind.
Okay.
So for ZOS to actually get to this is going to be a little while.
Okay.
But I'm getting to it because we're seeing this in the Z-Linux stuff right now. So let's see here. All right, so I've just gone back and shown what the...
Hey, can I interrupt just a minute?
Go for it.
I was debugging a compiler CodeGen issue, and I ended up in an IBM library routine, and it had vector store multiple and all those instructions in one of the IBM LE library routines.
Yes, I mean, even so the IBM library has them, and the IBM compiler uses them. So I mean, they're pretty much wide open. Now, IBM has all these things about forward and backward and all these other kind of things you can say, at least in Z. You're talking about Z-Linux, though, right? Joe, are you talking about Z-Linux or ZOS?
No, ZOS.
Really?
Yeah.
Well, if you run that and it's doing a Z14 instruction on our machine, that's not going to work. Because the VB perm does not exist on our machine. It gives you a OC1. But
This
anyway,
was a store multiple
the store multiple stuff,
load multiple.
that's it's hard to say, which one of those. I mean, that's all going to be at the Z13, so don't have a problem with it. All right, so this is sort of explaining what this thing does, which is what I showed in that first thing with pulling the bits down and stuff. We'll go a little more into the programming node here. So the idea is that if you do this thing once, if you've got, let's see, assume the 256 byte quantity is in registers 0 and 1. So here's 0, here's 1. And then you're using 2 as the thing, that middle row that's pulling out the bits. And then 4 and 5 here are going to hold the half word that's the result. So the first one's saying just do it, against the first register that's got the left half of this thing. And then we do this exclusive OR with what's in V3. Well, V3 says it contains, each byte of the vector contains 128, which is a hex 80. So when you do an exclusive OR byte by byte with a hex 80, all you're doing is reversing that top bit. And by doing that, all of the byte selectors that were pointing above 128 are now pointing below it. All the ones that were pointing below it are now pointing above it. And it's just a kind of tricky way to let you just keep looking at the left-hand side with the same mask. So we exclusive OR this thing. So 2 gets exclusive OR'd, with hex 80s. So now all the ones that were pointing low are pointing high, vice versa. And then we do the next guy with the right half of the thing, even though it's now on the left half. And then we OR those 2 together. So we'll see that a little better here. So here's the first instruction. And all these guys that are greater than 128 are going to pull out 0. They don't have any choice because this is, and remember, this is just in your mind, these are zeros. There aren't any actual zeros here. The instruction itself says take the 128-bit value in the vector register of this PARM and conceptually add 128 zeros after it. So we get zeros in all those places. Then when we do the exclusive OR with 128 in every one of those positions, he basically reverses them. So 24, something that had been pointing at the left-hand side, is now going to point at the right-hand side, and vice versa. So we just reversed all of these things in the selector. And now we select against the right-hand side, even though it's now looks like it's on the left, and we pull out those bits. So we get a different set of bits. And again, any ones that are greater, these are the ones that we've already selected the last time, but now they're just going to select a 0 because they're pointing over here. And we end up with this half word. And the weird thing about this half word is you'd expect it to be on the left or the right of the vector register. No, it's like in the middle, a little to the left of the vector register. I mean, it's in, like if you took the 64-bit and then just went a half word to the left, that's where it ends up. So you end up ORing these two together and you get the final answer. And basically, if you look back at the things, you'll see that this is the same bit pattern that you had gotten as if you had had a complete 256-bit thing of my original example.
I'm just imagining the developer being, the manager of the developer, like, can't you make it left justified? It's like, no, this makes it harder to crack.
Yeah, let's put it right in the middle. Well, and so the idea of a vector bit permute, and I looked to see whether Intel did these things in other places and stuff, and there's a lot of bit permute, kind of things out there in the world. Most of them doing with hashing and encryption and things like that. You could actually, if you did this 16 times, you'd have 16 half, or you could have basically all 256 bits completely shuffled, and then use a reverse mask to unshuffle them. So you could basically do a complete encryption of 256 bits that are you'd have a 2 to the 256 chance of unencrypting it. It'd be wild to kind of be able to figure out how to put those bits back, because it's not based on anything but this pattern that you could just make up. But that requires that the pattern that you use doesn't repeat. Right now, there's nothing to say that you couldn't have 152 in this position as well and pull out that same bit down here. But if you did this 16 times in a row, and every one of those basically had from 00 to Fox, then you'd have all 256 bits. And of course, you'd have to concatenate each of these half words as you finished to get the final result. But I could think of that as being another thing that you might want to do. And I saw that in some of the examples out there. All right, so that's basically the very first vector instruction that's in the book. And I didn't need to go into it, but I thought it was interesting. This is the one that actually hit me. So I was doing this thing where we had the WT tests or whatever that were, not WT, the one that were doing the signal handling stuff were not giving me the right answer. And it's because Alan, when he wrote this thing, had the signal handler look at the PSW and figure out what instruction had been called. The idea is that if you divide by 0, sometimes you'll get a invalid number, and sometimes you'll get a divide by 0. Yeah. And if you do 0 divided by 0, you get an invalid number. Well, SAS doesn't want to see invalid number. He wants to see divide by 0. Yep. So Alan took the PSW, looked at the instruction, and said, was it a divide? Was the operand 0? Oh, it was a divide by 0. Yep. I mean, God almighty. So I'm going through this thing to try to figure out, what's going on, why it's not working. And then I saw, oh, he's doing a vector full word divide and not a DD or one of the other divide registers, the other things that Alan had looked at. So I needed to change his code to handle this case. But that kind of led me into the whole thing. So let's just look at a very simple, this is the guy that we have. It's a D3. And we can't see because this thing's out of the way. Can I get rid of this?
The little pin to the right of stuff.
Right, yeah.
Just click on that?
Yep. Then move your mouse away.
Oh, great.
And then hit the same pin on that thing on the left. Yep, it's going to try and, you got to be really subtle.
There you go.
Now move it away.
Yeah. That doesn't matter. I can still see it. All right.
There it goes.
D3 divided by, D3 equals D1 divided by D0. So we're, purposely dividing by 0 here at this point. But this is what it ends up in the IBM compiler. And it's a little odd. So we've got another instruction. It's called vector load and replicate. Point out a couple things. We still got the RxB here because it's got a vector register, and you don't know whether it's 0 to 15 or 16 to 31. And that's what that is. There's a normal, base displacement to point to the second operand, and then there's this funny mask field. So we read the thing. It says this is two VL reps and then a divide. And basically what this is doing is loading vector register 0 and 1, and then we're going to divide 0 by 1 and store the result in 0, and then we're going to store the result of that. So the element size second operand is replicated into all elements of the first instruction. So I said you can have 16 elements if they're bytes. You can have 8 of them if they're half words, yada, yada, yada. But you just kind of fill them all up by saying replicate. It's whatever this base and displacement points to. There's only going to be one there, but we're going to put one of those in all the element fields. So based on this M3, that says how big the element size is. The M3 is not the same as the 3 here. So that 3 means double word. So how many double words fit in a vector register? Just 2 of them. So we've got 8 bytes stored at this location. We're going to stick those 8 bytes in both the first 8 bytes and the second 8 bytes of this vector register. Okay. We do the same thing for the second operand. And then we get down to the divide. So floating point elements or elements of the second operand are divided by the corresponding third operand, and the quotient are placed in the corresponding the first operand location. This is kind of a common thing that you're going to see in this code that Share seems to use and the vector stuff uses. We're used to having really just 2 registers when you're doing this kind of thing. Mm-hmm. You'd say, divide 0 by 1, and the result's going to be in 0. I don't need a third register. But a lot of these things, I guess maybe they had room to spare or whatever. They've all got these 6-byte instructions. So let's stick another register. Maybe you don't want to destroy that original one. Let's put it someplace else. In this case, he didn't. He stuck it back in 0. So you could have had something like a vector register divide just 0, 1. Mm-hmm. So you always have to remember there's 3 registers here. So in this case, the RxB is going to point. It's going to have 3 of those bits make a difference. And then you've got 2 masks. And it's like, oh, geez. So we got 2 masks in here, and if we look at the guy, he put a 3 and an 8. And when you look at him, that's the 3, that's the 8, but in the encoded code, that's the 3 and that's the 8. So you got to be real careful when you're looking at the dumps, to know the order of these things. But IBM's very consistent about numbering these operands and numbering them in the picture, numbering the bits.
Where's the order?
It's just that's the way it is, It probably made it, a nanosecond faster to do it that way. So let's talk about the M4 field. It specifies the floating point format. So right now in binary floating point, there's short format, which is 4 bytes. There's long format, which is 8 bytes, 64-bit, and then there's extended format, which is 128-bit. The new thing real here is that if you ever did an extended format floating point operation before, you had to use a pair of floating point registers. And all the instructions said, divide, extended 2 by 3 or something, and you always had to know, and and it was like weird when you only had 4 of them, because it was like you had to use 0 and 2, and you had to use 4 and 6. That was it. You were done. That was all you got. Now at least there are 16 floating point registers, so a pair of them isn't that horrible. But now you can have all 128 just hold that single floating point value, and you can use that in this instruction. If you had said 4 here instead of 3, and he would have done a 128-bit divide, which is pretty cool. So that's what the M4 is, basically telling you what the format of the floating point number is. So then we've got this M5, and it's not from Star Trek. M5, single element control. Only 1 bit of the mask is useful, so either it's an 8 or it's a 0. And the idea is that it's called the single element control. And this isn't the only one that has this. So all these vector things are saying, the whole purpose of them really is to do multiple things. It's a single instruction, multiple data. Well, now they're saying, oh, not so much multiple data. Let's just do 1 of these guys. So basically, if you have this one turned on, he's only going to look at the first element. And it's like, well, if all I'm going to look is at the first element, then why did I replicate these things into the top halves? Maybe I'm going to do something later. Let's check it out. So all it is just use the 0 indexed element in the vector. And IBM is very consistent about how they map these things. It's always from 0 to the left over to the right. So now we get to this next guy, and we're saying vector store element. So we got this, we did this divide, we stored the result in 0, we're going to store it back here. Again, the mask is going to tell us how big it is that it's not the mask this time. It's the instruction. So some of these things, it's actually the opcode that tells you how big the element is, rather than having a mask determine it. So in this case, vector store element grand means that I'm going to store 8 bytes. of this thing out of this guy. And then the 0, which is the mask, means, let's see, the element, it tells you which element you want to save. So in this case, since we're talking about grand, there's only 64-bit on the left or 64-bit on the right. So the element index can either be 0 or 1. So by saying 0 here, we're saying let's take the leftmost one, store that element. It's a grand. We're going to store 8 bytes at this position. And why you couldn't have just done load double, divide double, store double, there's no good reason. He just decided to use vector registers and vector instructions instead. Maybe it's a little faster, and that's why the compiler is generating those.
Have to do with the pipeline, maybe?
It might have to, well, you wouldn't think so, because, I mean, a load double and a divide double, how's that any different as far as the pipeline goes? You know, especially since it's using the overlaying same floating point registers.
Yeah, exactly.
You know, it's not like it's using different hardware.
Well, somebody else could use the other registers.
Right, you know, but I mean, he's using 0, 1 here. Yeah, so very odd. Okay, so in this case, I'm going to talk about a little bit. This is like what the share said you can use, and this is the kind of thing that we might take advantage of when we get down to it. Those other ones, it's like, why would I ever do this? Mm-hmm. Well, in this case, we're talking about Stirlen, and we're saying this is a faster way, and I know that Ed Jaffe has done this in the Phoenix code that he's got. He uses these vector instructions, and he sped up his Stirlen stuff, he said, by like 5 or something. Whoa. You know. So they're doing something internally that makes this stuff go really fast.
Yeah.
So we'll go into this a little bit more. This is actually the sample that I've got, so I don't want to go too far into it right now. One of the things to bring up, though, is this kind of odd business with this VLBB and LCBB. So BB means block boundary. So he's saying vector load up to block boundary. And the idea is that if you don't have to take a, what do you call it? An OC11 or something, an interrupt when you do a page in, then this stuff runs a lot faster. So this last part here says what you want the block boundary to be. In this case, it's 4K. So this is saying load 16 bytes, but maybe not. If you're right near a block boundary, only load up what's to the block boundary and then deal with the instruction after that. That way you don't have to take in the middle of your instruction a page in or something like that, and it speeds the whole thing up. Let's go a little further. So here it is, vector load to block boundary. These are the different boundaries you've got. I don't know why you'd want to pick any but 1K. I mean, right now that is what the page size is. They keep talking about doing 1 megabyte pages and stuff, but I'm not sure how close that is. But for this purposes, and all the examples I saw, they're using a 1K boundary for these things to do this stuff. So load it up. Now again, when you look at you'll see this thing loaded, but you won't know how many bytes it loaded. So they've got this other instruction that says put into register 1, not vector register 1, the number of bytes that you loaded in that previous one. There's no reason to run this instruction unless you just ran it after that other one. So you'll always see these kind of in pairs. So they're going to do load to block boundary and then tell me how many you loaded. Get back to this. Vector load to block boundary and then load count to block boundary. So I think it's the same exact thing. It's the same. You're going to use the same base and offset that you had before, the same mask to tell it what the boundary was. You're just saying, tell me how many bytes I really loaded because I need to know that because I don't want to have to calculate that myself.
How does it determine how many bytes it loads? I mean, it sounds like it's a random. I mean, what is it?
It's so I mean, if the virtual address is like Fox 8,
yeah,
and you said load 16 bytes, he's only going to load 8. So he's going to go up to the next 000.
To the next boundary.
Yeah, to the next boundary.
Okay.
So that's the whole boundary thing.
That's what that meant. Okay.
Yeah.
Gotcha.
So you'd get returned 8 in this case if you were at Fox 8 and you wanted to load this thing.
Yeah, that's useful.
Yeah, if you were below 16, then you'd load all of them, and this instruction would always return 16.
Yeah.
So
yeah,
that's the normal thing. And then we've got, so this is the killer one. So let's see if I can do this. Vector find element not equal. Well, that's what the base instruction is. But then you've got this mnemonic, that the assembler allows, which is vector find element not equal 0 block boundary.
Say that 10 times.
Yeah.
That's a long mnemonic.
So, proceeding from left to right. So this is like, similar to like the string search instruction that you've got that we used to have and that we used. In the old days, you would just do, compare logical immediate over and over again, or you would do a translate and test, which would tell you where you'd have a table that would show where the 0 would be, and we'd do a translate, and that would find it. There are all sorts of tricks that we used to use. Well, this is the latest, greatest trick to find a 0 in the block. So there's a particular bit on here that says, and you can use this to say, so find element not equal. So you're comparing two strings, 16 bytes at a time, and trying to decide out when it goes, and not even necessarily strings. They could be arrays of half words or arrays of full words or whatever. But he's looking for patterns to see when they go wrong. And the first time they differ, he returns that offset to you. Well, in the case of characters and character strings, that's fine. So if you're just comparing two things like a stir comp, you would do this thing and just load them up 16 bytes at a time until you found one that was wrong. And then it would return, oh, you got an offset other than 16. So you must have found a differing byte. And that's the end of your stir compare. Well, the 0 part on here says, or if it happens to be 0. So basically, what you're going to do here is compare the same string, 16 and 16. So he's looking at the same string, but since it's got that 0 on there, he's saying, and also if there happens to be a 0, stop then too. So this is kind of, the tricky way to do a C string and search, looking for a null. Two elements are not equal, the byte index of the leftmost not equal element placed in byte 7 of the first operand. Byte 7. There are 16 bytes of this, operand, but he's going to put it in byte 7 of the first operand. And zeros are stored in all the other bytes. Then there's a condition code that you can check as well. If the M5 field is 1, that tells you whether you want to set the condition code or not. If all amounts is zeros place the other, you just go 3 is set. So you really have to read this a few times to figure out, how you're going to code it, depending on what you're looking for. If you're just looking for a string 0, then it becomes kind of easy. If you're actually doing it to look for things that we're matching, it might be a little more complicated. So the 0 search bit is the M5. If that's 1 in M5, then we're also going to look for if it's 0. 0 is found second operand with a lower index than the other operand. So, still, they don't have to be pointing at the same string. They could be pointing at two different strings. Mm-hmm. But if that first string has a 0, he's going to stop. The byte index is 0 stored there. The M4 field gives the element size. So in this case, it's not just, it's this weird stuff. So one of the bits in the M5 says whether you want to do a 0 search, and the other one says whether you want the condition code set, and that's the M5. And then the M4 says what's the size of the elements. So you need to use the mnemonics. You're not going to be able to, it's going to be real hard to generate. Kevin has to do this part, where he figures out whether to set on these bits or not. We only have to sit there and say, Z and all the rest of that kind of stuff. So he does this stuff, and here's all the different mnemonics that we've got. So they're byte, half word, full word, and notice these are repeated: byte, half word, full word, byte, half word, full word. So those are all repeated. And then you've got whether you want the S, which is that. That's whether you want the condition code set or not. And then the Z is whether you want the 0 set or not. And then whether you want the 0 and the condition code set or not. So this is, vector find element not equal 0 byte set condition code. If you code all that, he'll set all those bits correctly, and you only have to give 3 vector registers as the rest of the thing. If you want to do the base one yourself, you can type in those numbers and get the same thing. Mm-hmm. And of course, if you leave the M5 off of there, it defaults as 0. All right, these are all the instructions. I just gave a list of them at the end, and you can look at these things. There's more of them in the Z14 than there were in the Z13. And floating point, there's decimal instructions. This is packed decimal. This isn't floating point decimal. And so that's kind of interesting. You can have really huge packed numbers. It's always been the case that you could have a larger packed number than you could have a floating point number. And now it's really the case. I mean, you can have a larger packed number than more than the atoms in the universe, I'm sure, if you go out to, 128 bits of this thing. Happy vectoring. All right.
Go vector yourself.
Go vector. So let's just look at a little example. So I originally wrote this code because I wanted to actually see the VX_perm thing, or VB_perm, the vector bit permute in action. And of course, I ran to this point and got a OC1 because we don't have a Z14. We've only got a Z13. When are we going to get a Z14, Ed?
Show me the money.
Show me the money. It's kind of amazing that we've got a Z13 because that was the first one that these things were on, So I mean,
So which vector operations are on Z13? But which is what on between Z13 and 14?
If you look at the last pop, they've got change bars next to them and stuff like that. And most of them were these bizarro things that were to do with encryption because this is like the encrypt everywhere thing.
Okay, so that's the main addition, whereas the new encryption.
Yeah, well, and also they went to different formats of floating point. So in the Z13, you can only do basically 64-bit floats for all this stuff.
Okay.
So there isn't 128, there isn't the half or the 32-bit floating point. They added some of that on there. I haven't looked at what a lot of the other differences were. I think it was just kind of filling in the stuff. This is what they could get out.
Yeah.
So I wrote this thing. So one thing to notice on here, so I'm loading stuff into vector registers from storage. Well, to do that, you really need, it's nice, they've given you a parm here that says whether the boundary is quad aligned or not. And they say it'll be faster if you quad align these options. So by saying 4, I'm saying source 1 is quad aligned. How many quad loops? And if you go down, source 4, let's go back here. I did a CNOP 016, which says, give me the first bit of 16-byte boundary, and the first byte of it, and that will quad align these guys. There's also a LQ. So in hex float, there's D, which we're all familiar with, where you can say D and then give some number, 3.64, whatever. And there's another one, E, which is for 32-bit floats. And then there's L for extended floating point, which are 128-bit floats. Well, for hex float, they also made an LQ, which is the same thing. It's a 128-bit hex floating point number, but it's quad aligned. And if you just want to quad align something without doing the CNOP, you could sit there and do Z0 LQ0 or a DS LQ, and that would quad align it. And then you can put in the LB. Now this is an IEEE 128-bit value. And I verified that actually works. I went on the internet to see what IEEE would look like in 128 bits. Kind of cool. So if you do that and you compile it, though, you get an assembler error unless you do sect align 16. And this was another thing that was kind of interesting to show. Normally when you call the assembler, we do parm, and we just give our parm statements here, and they're okay. With all of these GOF options and all the other stuff going on, you're real quickly going to run out of enough space on JCL to do that. So the ASMA opt DD is a reserved DD name, and you can put all your assembler options in line. That makes it a lot nicer. So you can do section align, which is basically, it says that every section that he starts, align it on a 16-byte boundary. And when you do that, the warning goes, it's actually, I think it's just a warning that you get if you code this thing and you don't have that, and you try to align this stuff. So that was the first one. And then I went into the share paper, that's basically the stuff we looked at before, we stepped through it. So, and here's what it looks like coming out. If there's anything. Notice when you do the CNOOP, so he started at 1E4, he needed to go up to 1F0, so he just put in no operation branch instructions for as many as he needed, to get in there. And then dead beef. So let's look at an example. So here's ASMIDF, and I want to do something else. breakpoint. Go. So I'm about to point to the string that I want to find the length of this string. And I hit go down 1, and R2 got set with that string. So if we look at that string, this is a very long string. Da, 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 da. So this is the guy that we're going to try to find the 0 for. And here's actually where the 0 is. So it's hex 70 down here. But notice it crosses a boundary. So we're going to see that boundary problem come up here when we do this kind of stuff. So let's go set 3, 6. Or I'm sorry, size. Yes, that's was just to make it look a little better. So as we step through these XGRK, you could have just done, XGR or XR. This is actually a 31-bit program, so I didn't need to use grand. That K is the new instructions that have to do with this idea of using 3 registers instead of 2. So if you said XR11, that would clear register 1. This is saying exclusive OR 1 and 1 and put the result in 1. Just like. But this was from the example, so I typed it in. So we're going to clear 1, we're going to clear 3, and as I step, you'll see, these registers change. Now we're going to do the VLB, so vector load to block boundary. So 0, 1, 2 is the base and the index. So 2 is pointing here, this first byte. 1 has 0 in it, and we're going to load the 16 bytes that start at that point into vector register 2. It'll show up here as floating point register 2. So I hit it once, and there we go. So you can see these same bytes are up here. And we have to imagine that the 8 bytes that follow it are just kind of running off the page here, because that's actually vector register 2, not floating point register 2.
Okay.
Now I want to know how many of these guys did I actually load. So we're going to do the LCBB and put that in R3. And we put it in R3, and it should say that it loaded 16, right? Because we haven't gotten to the boundary yet. We're only up to FE6, up to FF6. So he should have loaded all the way up to this point. So we hit F11, and R3 has 16. Great. So we got 16 bytes. We loaded that in. We're going to keep a running count. This is add logical grand register K. I mean, I've got 3 registers. It's the same thing as saying add register 1, 3. But here we go. So R1 now has got our running counter of our string length. We load it in first because it's also used as our index as we're going along. We'll have to back that out when we actually find the final null. But, we keep just one register kind of doing dual duty here. So now we're going to look for that first byte. So we've got 16 bytes in vector register 2. We're going to look for the 0 in it. And we do this instruction. And he's going to stick the result in the 7th byte of vector register 4. Here's vector register 4. Here's the 7th byte. And it's got an 8. What does that mean? Well, that means he found a null here. And I'm like, well, there isn't a null there. Well, what happened? All I can think is that this is a ASM-IDF bug. He must have loaded and reloaded floating point register 2 and wiped out the vector register 0. I mean, the right half of the vector register at this point. So we lost it. So I'm now going to take what's in offset 7 of that vector register, put it in register 4. There's register 4. Now I'm going to compare it to what's in R3, and he's going to say, is R3, higher than register 4? Yeah, it is. So I'm going to fall out of that loop. He's saying, great, your string is 8 bytes long. Well, that's wrong. So let's start again, and let's use a different vector register. Now we're loading in vector register 20. We say, how many bytes did we load? We loaded 10. We're keeping a running count of 10. Again, we're looking for the 0. We're going to put it in vector register 14, but we're not going to see that anywhere. ASM-IDF doesn't show it. But we're going to load what was in that 7th byte of vector register 14 into register 4, and sure enough, 10. So every time you get a 10 or a 16, you're going to say, I looked through the entire 16 bytes and I didn't find what I'm looking for. When I do this comparison, if it's not higher, then I'm going to loop again and loop back. So he's basically going to keep doing this. And notice the thing that he loads from is off that R1 is this, offset that we're using as an index into the thing. So R1 is the guy that keeps bouncing. R2 always points at the beginning of the string. R1's going to bounce as we go through. And he's going to keep going until finally we get to the point where when we load R4, it's not a 10. So we'll go through here. It's still a 10. Still a 10. There's a 6. So now we say, compare 3 to 4. Is it higher? Is 3 higher than 4? Yes, it is. Well, we must be done. So now we're going to subtract out that 10 that we added. Remember I said we're going to have to subtract it out later because we're using it as an index. We're not actually going to the next, section anymore. So let's back it out. And now we're going to add back in the R4, which is where the offset in that particular vector register we found the 0 is. And this should give us the length of the string. And if we step through a couple times, we get a nice WTO that says, the length was hex 70. We've done a Sterling. Amazing. Let's see here. I don't think there was anything else. Does anybody have any questions about this good stuff? I think I held it to under an hour. I'm pretty happy with myself. People are starting to fade. Joe, do you have any questions?
No, thank you.
Yeah, Joe fell asleep. So
I'm trying to keep it mute so you don't hear me cough.
I know. Let's see. There were a couple of. Is there anything else I want to mention? The quad, the 16 bits. No. I thought it was interesting. I was looking at CNOOP, the conditional no-op instruction. You can actually do a no-op to a greater boundary than 16 now. So they had a thing showing you can do a CNOOP 4094, 4096, which means conditionally no-op to the last 2 bytes of a page. And it would sit there and stick those 47s and 07s in there, as many times as you needed to, and then start it. And so you can only do that if it's assembled GOF. So apparently GOF needs that kind of thing, but I'm not sure, who else would want something like that. But I thought it was kind of interesting.
So other than ASM-IDF, does CPR or ZXTC support the vector stuff?
Well, we know that CPR does because Joe just added it.
Okay.
And he actually has a place where you can display the vector registers as well. He supports the instructions, showing them, and all that good stuff.
He added it for ZLX.
I support disassembly on LZX and MVS and Z64.
Okay.
So we got it both for CPR all over the place.
Right now you can only dump the registers on LZX.
You only put the vector register on LZX. That's all we really need them on, because it's going to be a while before we're talking about, when would we do this for MVS, and it's like no time soon really, because it's always a few years that we give the customers to get up to this stuff. There's no point in us putting it. They're just going to get an OC1 when they call it. What else? I haven't looked at the at DDD, and I've got it on my list here for IPCS to see whether they would show that kind of stuff.
That's true.
There are other places that we would want this in there. I've already shown. I'm going to open that bug with ASM-IDF because that really shouldn't do that. And but IBM, I think the stuff kind of fills in after they come out with the major stuff. The hardware guys come first, and then the software guys play catch up, to get this stuff going. Mm-hmm. But the POP is accurate and is actually pretty readable in these things. And it's just, a matter of knowing where to look and knowing that a lot of the instructions have these weird masks. That's the only real trick, I think, and how to see where the register numbers that are greater than 15 are, and that kind of good stuff. All right, so we're going to stop the presentation, say goodbye to everybody, and thank you very much for